Welcome! In this session, we'll be tackling an exciting problem titled Number of Music Playlists. This problem challenges us to create playlists under specific constraints, testing both our algorithmic creativity and understanding of combinatorics. Let's dive in and explore the approaches. Imagine a music streaming service that wants to generate playlists under specific rules. The challenge is to figure out how many different playlists can be created given n distinct songs. The playlist must have exactly goal songs, and every song must appear at least once. To prevent excessive repetition, a song can only be repeated if at least k other songs have been played since it was last used. Since the number of possible playlists can get extremely large, the result must be returned modulo 10⁻9 plus 7. The input includes three parameters: n, representing the total number of songs, goal, the length of the playlist, and k, the minimum number of songs that must intervene before a song can be repeated. The output is a single integer representing the number of valid playlists that can be created under these constraints. To understand the problem better, let's look at an example. Suppose n equals 3, goal is 3, and k is 1. This means we have 3 songs available, and the playlist must contain exactly 3 songs, with no song being repeated immediately. The output in this case is 6 because there are 6 valid playlists: A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. Each of these playlists satisfies the conditions: all 3 songs are included, and no song repeats too soon. Now let's consider another example where n equals 2, goal is 3, and k is 0. Here, we have 2 distinct songs, and the playlist length is 3. Since k is 0, songs can be repeated immediately. The 6 valid playlists in this case are A, B, A, B, A, B, 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 A, B, and B, B, A. Because the constraint on waiting before repeating is removed, we can generate playlists with consecutive repetitions, as long as the total length remains 3. Now let's look at an example where k restricts immediate repetition. Suppose n equals 2, goal is 3, and k is 1. This means a song can only be repeated after at least one other song has been played. In this case, there are only 2 valid playlists, A, B, A, and B, A, B. Playlists like A, B, or B, B, A are not allowed because they would violate the condition that one other song must intervene before a song is repeated. Finally, let's review the constraints and edge cases. The constraints specify that n in goal can range from 1 to 100, while k is between 0 and n1. Some edge cases to consider include when n equals 1, goal equals 1, and k equals 0, where there is only one possible playlist consisting of the single song. When goal is much larger than n, it becomes increasingly challenging to create valid playlists, especially with higher values of k. On the other hand, when k equals 0, songs can repeat freely, leading to the maximum number of possible playlists. These factors must be taken into account when designing a solution for the problem. To approach this problem, let's first consider the brute force method. The idea here is to generate all possible playlists of the required length, goal, using the n available songs. We would then count only those playlists that satisfy the given constraints, such as ensuring no song is repeated within a window of k songs. While this approach is straightforward conceptually, it involves generating all permutations of the songs and checking each one for validity. This quickly becomes computationally expensive, as the number of permutations grows factorially with the number of songs. Specifically, the time complexity of generating all permutations is O(n). And there's additional overhead for verifying the constraints. For large values of n and goal, this approach is not feasible. Instead, we turn to dynamic programming, which is far more efficient. By breaking the problem into subproblems, we can define a state dp, I, j, where I represents the number of unique songs used so far, and j represents the current length of the playlist. Ultimately, our goal is to compute dp, n, goal, which gives the total number of valid playlists of length goal using exactly n unique songs. Now, let's understand how we transition between states in our dynamic programming approach. If we add a new song to the playlist, we have ni choices, which are the songs that haven't been used yet. This contributes ni dp id1 j1 to the value of dp I, j, as we're extending the playlist by 1 with a new unique song. On the other hand, if we choose to repeat a song that's already been used, we need to ensure it hasn't been played in the last k positions. There are k valid choices for this, representing songs that are already part of the playlist but not recently played. This contributes at k *dp I j1 to dp I j. Combining these two possibilities, the recurrence relation becomes dp I j equals n I *dp I1 j1 plus and k *dp I j1. For boundary conditions, we define dp 0, 0 equals 1, as there's exactly one way to create a playlist of length 0 with 0 songs. Additionally, dp I j equals 0 if I greater than j or I greater than n, since we can't use more unique songs than the playlist length or the total songs available. With this setup, the dynamic programming approach has a time complexity of n** goal, since we calculate values for all combinations of I and j. The space complexity is also n** goal, due to the dp table, though we can reduce it to goal through space optimization by only storing the previous row of calculations. The key to solving this problem lies in the insight that it can be broken into smaller subproblems using the dynamic programming state dp I j. By recognizing that we can either add a new song or repeat a previously used one, we simplify the problem into manageable transitions. Additionally, to handle the potentially large results, we use modular arithmetic to ensure our computations remain efficient and within bounds. After considering various strategies, dynamic programming emerges as the best choice due to its balance of efficiency and clarity. While combinatorial methods, such as inclusion-exclusion, might provide a theoretical solution, they are more complex to implement and debug, making them less practical in many cases. By contrast, the dynamic programming approach is structured, easy to follow, and scalable to larger inputs. Compared to the brute force approach, which is computationally infeasible, and the combinatorial methods, which are harder to generalize, dynamic programming offers the most practical and reliable solution. It effectively balances clarity, correctness, and computational efficiency, making it the ideal strategy for this problem. In this problem, we are tasked with creating playlists of a specific length, called goal, using n unique songs. However, there's an important constraint: no song can repeat within the last k positions of the playlist. The objective is to calculate the total number of valid playlists that satisfy these conditions. To solve this efficiently, we use a dynamic programming approach. The key idea is to define dp I j as the number of ways to create a playlist of length I using exactly j unique songs. The base case is straightforward: there is exactly one way to create an empty playlist with no songs, so dp 0, 0 equals 1. From there, we build up the solution using transitions. If we add a new song to the playlist, we have n j options, as those songs haven't been used yet. On the other hand, if we reuse a previously used song, it must come from the j-k songs that are eligible, since songs within the last k positions cannot be reused. This ensures that we satisfy the constraints while systematically considering all possibilities. The dynamic programming transitions allow us to iteratively fill out the dp table. We iterate over playlist lengths, I, from 1 to goal. For each length, we also iterate over the number of unique songs used, j, which ranges from 1 to the smaller of I or n. To update the dp table, we consider two cases. First, when adding a new song, we use the relation dp I j plus equals dp I1 j1 asterisk n j plus 1. This accounts for the ways to extend a playlist of length I1 with j1 unique songs by adding one of the unused songs. Second, when reusing an old song, we use the relation dp I j plus equals dp I1 j asterisk max j k 0. Here, we extend a playlist of length I1 with j unique songs by reusing any of the eligible j-k songs. Once the table is fully populated, the final answer is stored in dp goal n, which represents the number of valid playlists of length goal using all n unique songs. For example, if we have 3 songs and need a playlist of length 4 without repeating any song within the last 2 positions, we would initialize the dp table and iteratively apply these transitions for each length and number of unique songs. This approach has several key insights. The constraint of avoiding repeated songs within the last k positions is effectively handled by limiting the reuse of songs to the j-k eligible ones. By breaking the problem into smaller subproblems, the use of dynamic programming saves us from the exponential complexity of directly generating all permutations. Proper initialization of dp, 0, 0, and restricting j to min, I, n, ensures that our table only includes valid states. The main data structure here is a 2D dp table, where dp, I, j, represents the number of ways to create a playlist of length I using j unique songs. The size of the table is goal plus 1 equals n plus 1, to accommodate all possible playlist lengths and unique song counts. This design allows us to systematically compute the solution for all subproblems. In terms of complexity, the time required is O, goal asterisk n, as we compute each state in the dp table through constant time operations. The space complexity is also O, goal asterisk n, to store the table, though optimizations can reduce this further. There are several edge cases to consider in this problem. For instance, if k equals 0, there are no restrictions on song reuse, and the total number of playlists is simply n caret goal, as any song can appear at any position. When n goal, it's impossible to create the playlist since there aren't enough unique songs, so the result is 0. If k is greater than or equal to n, no song can be reused at all, so the result becomes the number of permutations of n songs taken goal times. Lastly, if goal equals 0, the only valid playlist is the empty one, so the result is 1. To optimize further, modular arithmetic can be applied if the result needs to be computed modulo a large prime, which is common in competitive programming. Additionally, the space complexity can be reduced to O, n, by maintaining only the previous row of the dp table, instead of the entire table. This approach efficiently transforms the problem from a combinatorial counting challenge into a structured dp problem, leveraging overlapping subproblems and constraints to arrive at the solution. This implementation solves the problem of determining the number of valid playlists of length goal using n unique songs under the constraint that no song is repeated within the last k slots. We use dynamic programming to break the problem into smaller subproblems. The dp, I, j, table is defined such that each entry represents the number of playlists of length I that use exactly j unique songs. The table is initialized with dp 0, 0 equals 1, meaning there is one way to create an empty playlist with 0 songs. The outer loop iterates over the playlist length I from 1 to goal, and the inner loop processes the number of unique songs j from 1 to n. For each combination of I and j, we calculate the number of valid playlists using two cases. 1. Adding a new unique song asterisk here, we use a song that hasn't been used before. This contributes dp, I1, j1, asterisk, n, j1, to the count, where n, j1, is the number of remaining unused songs. 2. Reusing an existing song asterisk in this case, we add a song that has already been used, but it must not have been played within the last k slots. This contributes dp, I1, j, asterisk max, 0, jk, to the count, where max, 0, jk, ensures we only count valid reuses. The modulo operation, %mod, is applied to keep the calculations within the constraints of the problem. Finally, the result is stored in dp, goal, n, which represents the number of playlists of length goal using exactly n unique songs. The use of a dynamic programming table ensures that we compute the result efficiently, avoiding redundant calculations and adhering to the problem's constraints. This is the Java implementation of LeetCode problem number 920, number of music playlists. It mirrors the logic of the provided Python solution, using a dynamic programming approach. The function number music playlists computes the number of valid playlists of length goal that can be formed using exactly n unique songs, while adhering to the constraint that no song can repeat within k positions. Key differences include Java's type declarations, use of arrays instead of Python lists, and the % operator for modulo operations. The solution ensures efficiency and modular arithmetic to handle large numbers. To solve the problem of generating playlists of length goal with exactly n unique songs and no song repeated within the last k songs, we use a dynamic programming approach. Here, we define dp, I, j, as the number of playlists of length I that use exactly j unique songs. The core idea is to either add a new unique song or reuse an existing one. Adding a new unique song increases the count of unique songs used, and there are n, j1, songs available for this. On the other hand, reusing a song does not change the count of unique songs, but only jk songs can be reused since songs from the last k slots are restricted. Using these transitions, the recurrence relation becomes dp I, j equals the sum of two terms dp I1, j1 multiplied by the number of new songs available plus dp I1, j multiplied by the maximum number of reusable songs. The result is stored in dp goal n, which gives us the desired count of valid playlists. Now, let's explore specific examples to see how this works in practice. Consider the case where n equals 2, goal equals 3, and k equals 0. We begin by initializing a dp table with dimensions, goal plus 1, by n plus 1, setting dp 0, 0 to 1 as the base case. This represents the single way to create an empty playlist with 0 songs. For I equals 1, meaning playlists of length 1, we have one unique song to add. Adding a new unique song results in dp 1, 1 being calculated as dp 0, 0 multiplied by the number of available songs, which is 2. This gives dp 1, 1 a value of 2. For j equals 2, it's not yet possible to use two unique songs since we only have one song slot. Moving to I equals 2, playlists of length 2, we calculate dp 2, 1 by reusing songs. The value becomes dp 1, 1 multiplied by the maximum number of reusable songs, which is 1, resulting in dp 2, 1 equaling 2. For j equals 2, adding a new unique song gives dp 2, 2 a value of 2. At I equals 3, we start by calculating dp 3, 1, where we reuse songs to find its value. For I equals 3, when j equals 1, reusing songs gives dp 3, 1 as dp 2, 1 multiplied by the maximum reusable songs, which is still 1. This results in dp 3, 1 equaling 2. For j equals 2, adding a new unique song gives dp 3, 2 as dp 2, 1 multiplied by the number of available songs, which is 1, resulting in dp 3, 2 equaling 2. Summing all valid counts, the final answer for the given parameters is dp goal n, or dp 3, 2, which equals 6. Let's now take a look at another example where n equals 3, goal equals 3, and k equals 1. With this configuration, we begin by initializing the table. At I equals 1, adding a new song gives dp 1, 1 as 3. For I equals 2, adding a new song results in dp 2, 2 equaling 6, while reusing a song gives dp 2, 1 as 0, since reusing is restricted. At I equals 3, adding a new song gives dp 3, 3 a value of 6, while reusing songs for j equals 2 results in dp 3, 2 equaling 6 as well. The final answer for this second example is dp goal n, or dp 3, 3, which equals 6. Now, let's consider a slightly more complex case where n equals 3, goal equals 5, and k equals 2. Here, we simulate transitions across I values from 1 to 5, ensuring that we carefully track the addition of new songs and the reuse of existing ones. For I equals 4 and 5, the recurrence relation helps us dynamically calculate the counts while respecting the constraints on reusing songs within the last k slots. The final result for this configuration is dp 5, 3, which equals 36. Through these examples, we observe that adding new songs increases the count of unique songs, while reusing songs is limited by the value of k. To manage large results, we use modulo operations to prevent overflow. By leveraging the recurrence relation and carefully handling transitions, we can efficiently compute the number of valid playlists for any given input. To analyze the time complexity of this solution, we start by considering the nested loops in the algorithm. The outer loop, which corresponds to the length of the playlist, runs from 1 up to the goal, meaning it performs goal iterations. Within this, the inner loop iterates over the number of unique songs, running from 1 to n. This results in n iterations for each iteration of the outer loop. Inside these loops, the operations performed are basic arithmetic, such as addition, multiplication, and taking modulo. Each of these operations takes constant time, or O1. When we combine these factors, the total number of iterations becomes goal times n, and since each iteration involves constant time work, the overall time complexity of the solution is O, goal asterisk n. Importantly, this holds true in the best, average, and worst cases, as the number of iterations does not depend on the specific input values but solely on goal and n. Now, for the space complexity, we look at the main contributors, the dynamic programming table and temporary variables. The DP table is a two-dimensional structure with dimensions goal plus 1 by n plus 1. This means it requires memory proportional to the product of goal plus 1 and n plus 1, with each cell storing an integer that takes constant space, or O1. Therefore, the memory used by the DP table is O, goal asterisk n. Additionally, we use a few temporary variables for things like loop counters and intermediate results. However, these variables do not grow with the size of the input and are considered negligible, contributing only O1 to the space complexity. Combining these factors, the overall space complexity of the solution is O, goal asterisk n. Let's compare this optimized approach with a naive or brute force method. In a naive solution, we would attempt to generate all possible playlists and then check which ones satisfy the constraints. The number of ways to arrange goal songs from n unique songs grows exponentially, leading to a time complexity of O, n caret goal. Additionally, verifying the constraints for each playlist would add even more complexity, making this approach completely impractical for large input sizes. In contrast, the optimized dynamic programming approach avoids redundantly generating all playlists. Instead, it directly counts valid playlists by breaking the problem into smaller, overlapping subproblems. This reduces the time complexity to O, goal asterisk n, and the space complexity to O, goal asterisk n, a dramatic improvement that allows the solution to handle much larger inputs efficiently. Finally, let's solidify our understanding with a mathematical breakdown of the big O complexities. For time complexity, we know the algorithm involves two nested loops. The outer loop iterates goal times, and the inner loop iterates n times for each outer iteration. Since all operations inside the loops are constant time, the total time complexity becomes O, goal asterisk n. Turning to space complexity, the dominant factor is the size of the DP table, which has dimensions goal plus 1 by n plus 1. Ignoring constants, this gives us a space complexity of O, goal asterisk n. Therefore, both the time and space complexities of the solution are efficiently bounded at O, goal asterisk n, making it highly scalable for larger inputs. When working on the number of music playlists problem, there are a few common mistakes to watch out for. First, failing to properly enforce the constraint that a song can only reappear after a specific gap, like K, will lead to invalid playlists being included in your results. This violates the problem's requirements because the playlist must respect the gap restriction. Next, it's important to remember that this is a permutations problem, not combinations. The order of songs in a playlist matters, so treating the problem as combinations would produce incorrect outcomes. Additionally, edge cases like n goal or k equals goal are often overlooked. For instance, if the number of unique songs is less than the required playlist length, it's impossible to create a valid playlist. Missing these edge cases can lead to errors or runtime failures. Lastly, inefficient implementation of dynamic programming, such as using redundant computations or poorly optimized loops, can cause significant performance issues, especially for large inputs where n goal can go up to 10,000. Optimizing your solution is crucial to ensure it runs within acceptable time limits. Another common issue is incorrectly initializing the base cases in your dynamic programming table. For example, if you don't handle the scenario where no songs have been played yet, it can lead to cascading errors in your recurrence relations and ultimately produce incorrect results. When solving this problem in an interview, it's essential to recognize the constraints early. Specifically, the K constraint, which prevents songs from repeating too soon, heavily influences how states transition in your dynamic programming approach. Structuring the problem into states can help simplify it. For instance, you can define dp, I, j, as the number of ways to create a playlist of length j using I unique songs. Understanding how to transition between states by adding a new song or reusing an existing one is key to solving this efficiently. Additionally, for large inputs, modular arithmetic is necessary to prevent integer overflow, and your implementation must scale to handle n and goal up to 10,000 efficiently. Finally, be ready to explain trade-offs during an interview. You should articulate why dynamic programming is a better choice than brute force, emphasizing its polynomial time complexity compared to exponential alternatives. This problem shares similarities with other LeetCode problems that can help you build intuition. For example, LeetCode 1079, letter tile possibilities, also involves generating permutations under specific constraints. Another useful problem is LeetCode 62, unique paths, which is a foundational dynamic programming problem that teaches state-based thinking. LeetCode 91, Decode Ways, is another example that requires careful handling of state transitions and constraints. Finally, LeetCode 1411, Number of Ways to Paint an X3 Grid, combines combinatorics with state transitions, making it relevant for understanding this playlist problem. In terms of approaches, backtracking can be used as a brute force solution. It's simple to implement and works for small inputs, but its exponential time complexity makes it impractical for larger constraints. Dynamic programming, on the other hand, is much more efficient and systematically handles constraints like K and the playlist length. However, debugging the state transitions and ensuring the base cases are correct can be challenging, so extra attention is needed during implementation. Another alternative to consider is a mathematical combinatorics approach. This method can be the most optimal in terms of time complexity since the calculations are often O(1). However, deriving the correct formula to account for all constraints, such as the no-repeat gap K, can be quite difficult. Additionally, this approach is less intuitive and harder to implement correctly, especially under the time pressure of an interview. While it's worth understanding for theoretical completeness, most candidates will find dynamic programming to be more practical and reliable for this problem. Great job! We've successfully navigated the number of music playlists problem, reviewing key concepts and strategies. Keep practicing similar problems to solidify your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!